Hi there, AP Calc students. It's time for our first online lesson. We're starting in chapter 3, of course, and this is entitled The Derivative of a Function. So here's our official definition for the derivative right here. Make sure to write this down. We'll be using this quite a bit. And eventually we'll be learning some shortcuts, but this is the official definition of the derivative. And again, as we've emphasized and will emphasize, this is just a fancy way of doing slope. But the idea is that it is the slope at a point. So this is really just a change in y over change in x. Here's this f of x plus h, that's a y value. F of x is a y value, so change in y up here, and my change in x is represented by this h value here. And the idea is that we want this h to keep getting smaller and smaller, and therefore we'll eventually have the slope at a smaller and smaller interval until we have that slope at a point. So good for you to write this definition down. Those of you that are coming from pre-calculus will remember this. We did this with limits. So now we formally define this slope at a point as something called the derivative. So let's actually find the derivative of f of x equals x squared plus 3. So again, pre-calc students, if you've just had this, you'll recognize how we do this. So we say the limit as h approaches 0 of that function. Now the idea is we're always going to substitute that f of x plus h. We're going to substitute x plus h in place of x. So, and we'll be practicing this in class, but this will be x plus h squared minus 3. But now we have to subtract the original function here, and that's going to be x squared minus 3. And all this, of course, is over h. Sometimes I won't write the over h just to save a little bit of room here. Okay? Now that's going to be equal. I'm going to wait to not write this limit expression out all the time. If I square x plus h, I'm going to get x squared plus 2xh plus h squared. Then I have minus 3. So that's that first part here. I just expanded out this x plus h squared. And then here's my minus 3. Now, notice to keep going here, when I have a minus sign in front of parentheses or in front of brackets, it's going to be minus x squared plus 3. Now I think you can see what's going to happen here, and this will happen pretty much all the time. Some stuff will cancel out. Here's an x squared minus x squared. Here's a minus 3 plus 3. So that kind of thing happens almost all the time when we do this derivative by the definition. So what I have left then is 2xh plus h squared. Now keep in mind this is still all over h. Can I do any canceling here? Not quite yet, until I factor out an h from my top expression here. And now when I am multiplying and dividing by h, now I can go ahead and cancel these two h's out. So what I have left at this point is, keep in mind this is still a limit expression, so I have the limit as h approaches 0 of now 2x plus h. So we say that because h gets so close to 0, we're going to basically call this 0, and my answer here will end up to be 2x. Very powerful, because now no matter what x is, we can figure out what that slope at that point will be. In other words, the derivative. Now here's another definition of a derivative, and notice here we have an a value in here. So rather than h approaching 0, we say that x approaches this particular a value. Let's just do the same thing with this function and see if we get the same result. Let's see, I think I'm going to change colors here just for fun. So the f of x in this case will be, well, this time I'm going to say the limit as x approaches a. And so now I take my original function, which is going to be x squared minus 3, but then I subtract. Now here's where I put a in place of x, so that's going to be a squared minus 3, and all of that over x minus a. Well, again, we see that in my numerator here I'll have x squared minus 3 minus a squared plus 3. Again, the minus in front of parentheses does that. And once again, you can probably notice that I'm going to be able to cancel out some stuff here. Here's a minus 3 and a plus 3, so that cancels out. And so what I have left then is x squared minus a squared. And don't forget we have that x minus a under here. Well, can I just cancel these guys out? It's an x here and an a there. No, don't do that because of that minus sign. What I can do though, and you may remember this from your algebra days, and we'll talk quite a bit about these algebraic techniques. Notice my numerator is actually a difference of squares. X minus a times x plus a. Then I have my x minus a in the denominator. Now when I do this, now I can cancel out those because they're multiplied and divided. And my final answer ends up to be x plus a. And keep in mind, what this is we're still thinking about this as x approaches a. So as x gets closer and closer to a, what we really have here then is basically a plus a, and of course that equals 2a. You might recall the last time we did this, the other method, we got 2x. Here we get 2a. Basically the same thing. So just an alternative way of figuring out the derivative or the slope at a particular point. Alright, just looking at some notation here that we'll use for derivatives. The first set of notation, which is this prime stuff, looks like an apostrophe. We say the f prime of x or y prime. That's attributed to this guy, and pretty famous guy, Sir Isaac Newton. He came up with that notation. And the other notation here, which is the dy over dx or df over dx or the d over dx, all this is attributed to this guy named Leibniz. I think I am spelling that approximately correctly. These are two guys who are considered the father of calculus. They were both working at about the same time. It might be interesting for you to do a little research on each of these guys. I am really impressed with their hairdos. They look like pretty dashing dudes, I think, as well. But anyway, that's all kind of notation. We'll see all this notation. Our textbook will kind of spread this around so you're used to using both types of notation for the derivative. Alright, you can actually also get derivatives from graphs, and this is kind of an important thing to think about. Now remember, whenever you see that word derivative, you should think that it means slope, as we've talked about in class and we'll talk about in the future. Derivative is slope. So what I have graphed here, I have a piecewise function that I have graphed on my calculator. We'll be doing quite a few of these. So y equals negative 2x, that's this one here, only graphed when x is less than 1. Straight line with a slope of negative 2. On the right side here we have y equals x, the slope of 1, and that's graphed when x is greater than or equal to 1. Now, what would the derivative look like here? Well, eventually we'll learn some shortcuts, but again, if we just keep in mind that derivative means slope, so the slope of this line is negative 2, we'll actually write that as a straight line. Y equals negative 2, and it is graph when x is less than 1. And then in similar fashion, since the slope of this, y equals x, is actually a slope of 1, we'll graph that. Y equals 1, again a constant or a straight horizontal line, graphed when x is greater than or equal to 1. So that's the slope. If this is my original function f of x, like this would be my f prime of x, or my derivative would look like this graph right there. Alright, same type of thing over here. If I had This is going to be my graph y equals x squared. Pretty traditional parabola graph. And if you imagine looking at various points here, we'd certainly think that everything greater than 0 would have a positive slope. Everything less than 0 over here looks like it would have a negative slope. So my other graph here is actually the derivative of this. I'll write it like this, y prime, and this is going to be the line 2x. And you might say, well, doesn't this have the same slope throughout, a slope of 2? It does, but if we think about my y values are actually going to be negative when we're less than 0, just like all my slopes at a point here would be negative when I'm less than 0. And then sure enough, when x is greater than 0 over here, all the positive y values are graphed, and that's when the positive slopes would occur over here. So again, important to start seeing the connection here between the original function and its derivative. Now this will take you a while to write down, so you might want to pause the video and write this stuff down, but kind of good stuff. We'll spend a lot of time trying to figure out whether a function is differentiable or not. Can you find derivatives at certain points? And here it says that it is if we have a right-hand derivative at a. Again, that's kind of like coming in from the right that we might know of. And the left-hand derivative coming in from the left. Again, if those things exist, they might exist at endpoints, or they might exist actually in the interior part of the function. So notice that this is kind of an important paragraph down here. Right-hand and left-hand derivatives may be defined at any point of a function's domain. So it could be an endpoint, could be an interior point, whatever. But if they disagree at that point, then the function is not differentiable. And you may remember, as we talked about limits, in order for a limit to exist, that left-hand limit had to be the same as the right-hand limit. Kind of the same thing here. In order for a function to have a derivative or be differentiable, these left-hand limit and right-hand limits have to agree. And we'll be doing some work with that. Here's a good example here. Let me write this down. We have a function here. This is going to be on the left side here. Again, a portion of the graph y equals x squared. On the right side we have y equals 2x. We saw there was a connection between those. However, as we think about the slope coming in here, now as we come in here from the right here, well, the slope in this case is always going to be the same. This is a straight line, so this is constant. So the slope of this is actually going to be 2. However, when I come in from the left side here on this y equals x squared, actually the slope as we get very close to 0 here will also be 0. We could do that algebraically, coming in from the left and the right. I'm not going to take the time to do that. We might do that in class a bit. But here's a case where, even though this is a continuous function, this is a function that's not differentiable at 0 anyway, because these two slopes do not agree coming in from opposite sides. Alright, thanks for hanging in there, everybody. This is a little bit longer video, as you might guess will happen in calculus stuff, but we'll see if this works, and we'll work on this in class tomorrow. Bye now.